This set of notes is about synapses and neurotransmitters that are used in synapses. It's my absolute favorite set of notes. It's my favorite thing to talk about. It's got everything in there, why you're dumb, why you're anxious, why you're brilliant, why you like sex, why you like chocolate, whatever. It's all in there. Synapses and neurotransmitters. But before we get into the specifics of synapse, I want to acknowledge that A, you need to know what a synapse is, right? And a synapse is the site at which a neuron communicates with the next cell, yes? And if you are in the brain, then neurons are communicating with neurons, yeah? But neurons can also boss around other kinds of tissues. Which other ones? Muscle and glands, yes. Okay. In this set of notes, we are going to focus on neuron-to-neuron communication, and the next set of notes we'll talk about neuron-to-muscle communication, and we really never talk about neuroglandular communication. Okay, so synapses are going to be the site of neuron communication, and we talked about the fact that you can form new synapses even if you can't form any approachable number of new neurons. So, types of synapses. First thing is that there is a type of synapse that would go more quickly than the ones we are talking about. And the type of synapse that would go more quickly than the one where you have to release neurotransmitters to communicate to the next cell is if you took two neurons and you stuck them together with gap junctions, then can you see that you could pretty much have a continuous action potential from one neuron to the next, yeah? That's called an electrical synapse, and those are all fine, but it also means that cell A and cell B have to do exactly the same thing, doesn't it? If they communicate via ions and one was depolarizing and the other one depolarizes, you sure as heck don't want all of your neurons on at the same time, right? If you turn one on, then they'll all be on, right? You would have every single song lyric that you'd ever learned running through your head when you were trying to go to sleep, right? And you would literally murder someone in your family, is what you would do. So electrical synapses use gap junctions, but that is not what generally happens in your brain as an adult. As a child, well, as an embryo/fetus, when your brain was being put together so that you had all the proper connections, everything was put together with electrical synapses and gap junctions. But then as your brain matured and you actually had to start doing things like wiggle this part and not that part, right? Then they pulled apart, right? And they start communicating between the two cells with neurotransmitters, yeah? And that is a different kind of synapse. This kind of synapse that we're going to be talking about now is called a chemical synapse. And the chemical synapse is the most common type of synapse that you have. So let's just give you a visual to understand it. Here is cell A and here is cell B, yeah? And what is going to happen between cell A and cell B is I have the capacity to release neurotransmitters that communicate between the two of them. So these two cells are going to be microscopically separated. What should be in between them in this space right here? What is in there? Yeah, just interstitial fluid. But it's microscopically separated. It's like micrometers wide, right? So they look like they're attached, but they're actually not attached, and you can communicate different things between the two of them. So that is called a synapse, and this one's going to be a chemical synapse because it uses chemical messengers. And the ones that we're going to be dealing with in this semester, in this set of notes are called true synapses, and it's neuron-to-neuron communication. There are also neuroglandular junctions and neuromuscular junctions. We'll be talking about neuromuscular junctions next. Is that okay? Okay, so what we're going to need to do is we're going to have to put this together with the stuff that we did last time and so get some terminology down. So let's look at the basic anatomy of a chemical synapse, and we'll sort of build one on the board as we do. Okay, so a chemical synapse, let's say we've got two cells communicating with one another. So we'll start with cell A. And cell B. Now, because you have had enough anatomy and physiology, you can look at any two neurons in series and tell me which direction information is flowing between them, can't you? Yeah, so information is flowing this direction, right? Everybody knows that because you know dendrites in, axon out. Okay, with that in mind, now you can label one of these the presynaptic neuron and the other one the postsynaptic. Which one's this? Presynaptic. And this one is postsynaptic. I will tell you that saying pre when you mean pre and post when you mean post will be really important for doing well on the subnotes, right? The pre will be doing different things than the post. Okay, so the direction of information flow is there. And then the synapse, what is the synapse? It's actually bigger than you think. So the synapse isn't just this space right here. The synapse is the entire region where the pre and the post can communicate. So that whole thing is the synapse. And then the area right between them that's filled with interstitial fluid is called what? Can I remember? Yes, synaptic cleft, exactly. Okay, so we got a couple more players to learn, and then we're going to put this together with the set of notes that we did last time. So I want to use a pitcher-catcher-ball analogy with this. So what's going to happen is this cell, we know that if this one gets sufficiently depolarized that you hit threshold here, you're going to get an action potential, yes? And the action potential is going to go without ceasing all the way to the end of the cell, to this region of the cell. And the region at the end of the cell, if this is my axon, these are my axon telodendria, yeah? And the tips of my fingers are what? What are those called? Axon terminals, yes, okay? So the fingertips right here are called axon terminals. And the axon terminals are usually kind of bulbous. They look like ET fingers, right? Skinny and then bulby on the end. Anybody remember why they're bulby? What's stored in there? Yes, neurotransmitters are stored in what we call synaptic vesicles. And they have neurotransmitters in them. Okay? So, action potential. All the way down, when the action potential hits the end, I'll teach you to fizz in just a second. What's going to happen is it will cause exocytosis of the neurotransmitters that were stored there, and they will be released into the synapse. Pitcher. Ball. Yeah? Catcher, but he needs a mitt. What do you think the mitt actually represents? Receptors on the postsynaptic cell. Does that make sense? Postsynaptic cell is going to have receptors and therefore can respond. Okay? So let's look at the figure here, and then we'll add just a little bit more detail, and then we'll add some players that you haven't met yet. So here's the presynaptic neuron, and this is specifically the axon terminal, the bulbous portion, right? This is the neurotransmitters that were made and stored in vesicles right here. The neurotransmitters are going to be released into the synaptic cleft and bind to this receptor on the postsynaptic cell. Okay, so now before we go add any more detail, what I want you to see is pitcher, catcher, ball, mitt. So what we are seeing right here is that synaptic transmission is always going to be one way across a synapse. Does anybody see anything structural, even from my bad drawing, that will prevent you from sending the signal backwards?
No axon.
No axon? What else is there? I mean, even if you could get the ball back, there's no receptors. Exactly, right? So you can't make the stimulus go back that direction, even if you could get an action potential to go, which you can't, right? So you can't cause a response the other way. So you could, for instance, roll the ball back to the pitcher, right? But you're not going to cause the same response as hitting the mitt. Does that make sense? Okay, so synaptic transmission is unidirectional. Now, just because I hope this is obvious, but it might not be. This is presynaptic and postsynaptic for this synapse, yes? But that doesn't mean that this one can't be presynaptic for the next synapse, yeah? So it's per synapse. You're dealing with at the synapse, yeah? Okay, so transmission is always one way, no receptors, no capacity to respond to it. So now let's add in a little bit more detail and put some fizz in here, okay? So a neuron is separated from its neighboring neuron by the synaptic cleft, and it's filled with interstitial fluid, and it's a microscopic space. The action potential, let's see if this makes sense. The action potential cannot jump across the space. Does it make sense to you if I say that an action potential is a phenomenon that happens on a cell membrane? Yeah, and in the absence of a cell membrane, can you have an action potential? No, because it's actually a depolarizing change across the cell membrane. So if you don't have a cell membrane, you can't have an action potential. The only way that you could get a continuous action potential is to stick them together with gap junctions. So it can't jump the space. So what does it do? I get an action potential that causes neurotransmitters to be released here, how do I get that one to an action potential? And the answer is you have to start the whole damn story over again every single time. So what's going to happen is this one, okay, is going to be bombarded with chemical, neurotransmitter. If that chemical binds to and opens a sufficient number chemical-gated sodium channels, then you can hit threshold here, yes, and it will get you another one which will dump more chemical. So it doesn't jump the space. You started the story last time. We told the entire story of how you get an action potential, and now I'm telling you that you have to do that every single time on every single cell. That makes sense? So it can't jump across the space because there's no cell membrane to have an action potential on. Okay, so let's talk about what it actually does do. What it does do is oh, you know this, but the space is bridged with chemical messengers, and what type are they? What type of chemical messenger? Neurotransmitters, exactly. So when the action potential reaches the axon terminal of the presynaptic neuron, you're going to introduce a new kind of channel that you didn't know about before. And this new kind of channel only exists on axon terminals, only at the fingertips. So you're never going to get it as you're going down. It will always get hit last. And these are voltage-gated calcium channels that open in response to depolarization, right? And this is going to be the last place to depolarize in the cell, okay? So voltage-gated calcium channels that exist here. When they open, calcium is going to move down its electrochemical gradient. Calcium is high in the extracellular fluid, and remember, it's negatively charged on the inside of the cell. So where does calcium want to move? Into the cell, but into which? Pre or postsynaptic? Into the presynaptic cell. Yes? And it's that increase in calcium concentration in the presynaptic cell that triggers exocytosis, as long as you have ATP. And by the way, you have a boatload of mitochondria down there, so you generally do have ATP. Does that make sense? So it triggers exocytosis of the neurotransmitter. And so let's look at a functional diagram now. Okay, so I've got my action potential. Yeah, when the action potential hits the end, it opens your voltage-gated calcium channels. Calcium rushes down its electrochemical gradient, right? Causes exocytosis of the neurotransmitter, which is these little purple triangles. And remember, you don't lose your vesicle, right? The vesicle stays, right? You just dump the neurotransmitter. And then the neurotransmitter will just diffuse across the synaptic cleft. It's microscopic in distance. So you get a pretty fast response, and it will bind to the receptor on the postsynaptic cell. Good? Bind to the receptor on the postsynaptic cell? Okay. So what neurotransmitter was it? How do you know? Well, the neurotransmitter usually, this is usually what's true. A single neuron makes, stores, and releases a single neurotransmitter. So for instance, if I was a serotonin neuron, that's what I do. I make, store, and release serotonin. If I was a dopamine neuron, I make, store, and release dopamine, right? So, although, of course, because in biology, every time you think you know the rules, some yahoo finds an exception. They just recently found that there are a couple of neurons that make, store, and release two different neurotransmitters. And we literally have no idea how they decide which one to release. Okay, so we're going to pretend that doesn't happen, la 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 la, until somebody figures out what the hell is going on. Because most of them just do make, store, and release a single neurotransmitter. So basically what do you release? Exactly what you had there. That's what you release. Okay? So neurotransmitter examples, and we'll get into some more of them today. Some of the neurotransmitters, acetylcholine, GABA, which is gamma-aminobutyric acid, which you can call it GABA, it's fine. No point in making you learn the name if you don't know what the chemistry means, right? And then epinephrine, norepinephrine, dopamine, there's a bunch of them. By the time we're finished with this set of notes, I think we learn 20 neurotransmitters, maybe even fewer. There are at least 60 that we really understand the function of. There's at least 100 that we know of, but we don't know all of those last 40 do. Which ones am I going to teach you? The ones that I know are currently clinically significant or I predict will be in the future. Right? They have to be somehow relevant, and we have to know enough about them for you to study them. Otherwise, it's just pointless memorization. Go ahead.
So this is why everybody is very different, because each neurotransmitter is different.
Yes. You have this basic recipe in your head for your brain functionality, which is a slight difference between you and everyone else.
So
yes.
do you feel like we're born like that? Like
your neurochemistry is dramatically affected by your environment. So if that doesn't make any sense to you, then whenever you have sex, of course you release dopamine and you're like, oh, I'm happy. And then when something horrible happens to you, your serotonin level can drop, like if a death occurs in your family. So you have like the basic genetic predisposition, which is like your soup, right? That's impacted by the environmental constraints. And then if you do stuff like decide you're going to be a crackhead, then you're really going to dramatically affect them in a way that's relatively predictable. So you get your soup, right? You inherit your genetic soup, which is impacted by your environment. And we'll talk about that too, because we'll talk about the mind-body connection, but instead of talking about it like a yoga teacher, we'll talk about it like a physiologist, right? Okay? And every once in a while you run into a yoga teacher who is a physiologist, and that's the class I'm going to, just so you know. I'm like, you are so smart and bendy. Okay, so we'll get back to neurotransmitters in just a second. Okay, so the neurotransmitter, whatever it is, binds to a protein receptor, and the protein receptor is usually a ligand or chemical gated ion channel, yeah? If it's a sodium channel and you bind to it and open it, you will what polarize the postsynaptic cell? Depolarize. If it binds to and opens instead a potassium channel, you will what polarize the postsynaptic cell? Hyperpolarize. Okay, so what it's going to generally do is bind to and open a sodium channel or a potassium channel. We'll talk about exceptions to that in just a second. Before we go any further, let me just give you a visual to show you sort of what this looks like. Oops, that's not what I meant to do. And that is, because I know some of you guys are really, really people who benefit from animations. Okay, so this is a chemical synapse, right? Presynaptic, postsynaptic, axon terminal. What do you think those are? Those are voltage-gated calcium channels, yeah? And this is the postsynaptic cell membrane, and those are going to be the receptors. So what you're going to see is when the action potential depolarizes those voltage-gated calcium channels, you will open them, and then calcium will move into the axon terminals down its electrochemical gradient. It's that influx of calcium that will cause exocytosis of the neurotransmitter, yeah? And then the neurotransmitter happens to be acetylcholine here, diffuses across the synaptic cleft, and binds to, in this instance, and opens a chemical or ligand-gated sodium channel. And sodium moves into the postsynaptic cell, what polarizing it? Depolarizing it, right? It doesn't have to be depolarizing. This particular synapse was just a depolarizing synapse. Is that okay with you guys? Okay, so let's talk about what you can do to the postsynaptic cell. So you can look at what the synapse is doing, and you can say that's an excitatory synapse or an inhibitory synapse. And it really depends on whether you bind to and open a sodium channel. Then can you see that you're getting closer to an action potential and therefore excitatory? I'm not saying you're going to get one. I'm saying it's the right direction. Yeah? But if you bind to and open a potassium channel, you're getting further away from an action potential, and so you're inhibiting it. Yes? Okay? So if you depolarize, you're getting close to threshold. If you hyperpolarize, you're getting away from threshold. Just so you know, that's the primary mechanism by which your brain turns things on and off. Right? You can either depolarize if you're trying to get to an action potential, or if you definitely don't want that to be on right now, you hyperpolarize it over and over again so it doesn't get to an action potential. Does that make sense? Okay, so now what does it look like? What's it called when you have an excitatory synapse? If the neurotransmitter binds to and opens a sodium channel, it causes depolarization and excitation of the postsynaptic neuron. So let me show you what that looks like on a graph. So this one. Okay, so the green is supposed to be excitatory and the red is supposed to be inhibitory, okay? So if I just release the neurotransmitter at A, the excitatory synapse, I get a little bit of a depolarization, yeah? Same thing as if I release it at B, okay? At this particular point, you can call this an EPSP, an excitatory postsynaptic, because that's where it's occurring, potential. Now I want you to add one more word to it. Is that a graded potential or an action potential? It's graded, yes. Okay? It's an excitatory postsynaptic potential, but I want you to understand that it's graded. Okay? It doesn't mean you get an action potential. Remember, before you hit threshold, you're still graded. Yeah? Okay, so that's an EPSP. And this synapse right here would be described as an excitatory synapse. And what happened on the postsynaptic cell would be described as an EPSP, an excitatory postsynaptic potential. Good? Okay, so if the EPSP hits threshold at the axon hillock, then you'll get an action potential. But it doesn't always. You can have depolarizing graded potentials that don't hit threshold. Okay, and then inhibitory synapse. An inhibitory synapse is if the neurotransmitter instead, this would be a different synapse because the same neurotransmitter is not going to be excitatory and inhibitory at a single synapse. Okay, so if this neurotransmitter that I released bound to and opened a potassium channel, it would do this, right? And you would describe the synapse as inhibitory, and you would describe what happened on the postsynaptic cell as an IPSP, inhibitory postsynaptic potential. Does that make sense? IPSP, okay? So EPSPs and IPSPs, and we will be talking about them. Okay, so you would use an IPSP if you wanted to turn the cell down or off or make it far less likely that it would get an action potential. Now, for those of you who understand the ion thing really well, I will tell you that you don't always have to use sodium to start EPSPs. You can use any positive ion that moves in, right? You don't always have to use potassium to start IPSPs. Sodium and potassium, though, are very dependable because we work really hard to keep the concentration gradients what they are. But see if this makes sense to you. You can also cause an IPSP by opening a chloride channel because chloride will move in. It's a negatively charged ion that will move in. And that will hyperpolarize the neuron, won't it? Okay? Okay. But just so you know, I will always sort of, throughout this entire semester, unless it's relevant to tell you that we need to use something other than sodium or potassium, I'll always just sort of let you think that it's sodium or potassium, and then you'll know on occasion you can use other stuff. When we get to the cardiovascular system, you use sodium and calcium for depolarization. It becomes relevant. I just don't want you to think that it's a hard and fast rule that you have to move a particular ion to cause depolarization and hyperpolarization. Okay, so let's reinforce this by telling you something that is clinically relevant, and that is that, go ahead.
Yeah, the excitatory synapse, the number one,
Mm-hmm.
it says here that if it hits threshold, it will cause action potential.
Yes.
But you said it's graded.
It's graded, always graded before it hits threshold, right? If you hit threshold with an EPSP, then you will become an action potential.
Yeah, it says action potential, then it gives the name EPSP.
Oh, that's just because you have the old set of notes. That's why I flipped them around because I thought it would make more sense the other way. Go ahead.
So then when you're talking like a couple weeks ago in class, when we have that and it goes all the way down, like that's why it has to be such a strong action potential to make sure that it continues into the next synapse, right?
Well, it doesn't matter. Remember, there's no such thing as a strong action potential. You just have to hit threshold here. So Vivian, one more time with you. If you have an EPSP that's strong enough on the cell body that you depolarize to here, it's still called an EPSP, but once it hits threshold, then it becomes an action potential. So your question is you need it strong because you won't release neurotransmitters unless you hit threshold. But if you needed a lot of it, instead of just doing one action potential, you would do 5 or 10 over a period of time. Yeah? And then you get more in the synapse. Got it? Okay, so did that get your question?
Yes.
Okay.
I have to check it.
Well, I mean, they're not dramatically different. I just read through them again night before last, and I thought, oh, there's like a clearer way to say that. So I fixed it specifically because I thought someone might be confused. And I was right. I was late, but I was right. Okay, so there is a disorder in which what you have is a storm of action potentials that generally starts occurring in one side of the brain, and it can become such a massive electrical storm of depolarization that it goes all the way through one side of the brain, across the corpus callosum, and causes a storm on the other side of the brain. And by storm, I mean depolarization after depolarization after depolarization. And because the brain, of course, controls skeletal muscle contraction, it can also cause skeletal muscle contraction. And this is a grand mal seizure with epilepsy, okay? With epilepsy. There's a million different reasons that you could have epilepsy. It could have been because of an injury. It could be because of drug use. It could be because of genetics. But what happens is you get this massive electrical storm. So how is this related to it? One of the first tier treatments for epilepsy is that they use a drug. This one is called primidone that actually slightly hyperpolarizes your neurons at rest. Can you see why that could help avoid that electrical depolarization storm? Does that make sense to you? Slightly hyperpolarizes your neurons at rest, so you're less likely to actually have this massive wave of depolarization. So why the heck do people always go off this medication when it is working to keep grand mal seizures away?
Because they think, you know, oh, I'm better.
Well, it's that too, but also if you're decreasing inappropriate action potentials, don't you think you're also decreasing some appropriate action potentials? And they end up feeling mentally and physically lethargic and kind of stupid and not very responsive. And so the general pattern usually goes, I have seizures, I go on the medication, I feel dumb as a box of rocks, and I don't care about anything. And then I'm like tired of feeling like this, so I go off the medication, I have grand mal seizures over and over and over and over again. Okay? And you can like have some compassion. Imagine like somebody just said, okay, you can feel okay, but you have to lose 15 IQ points. You cool with that? Really, I don't understand the question. Go ahead.
They have dogs that can sense when a person has these epileptic seizures.
Yeah.
Have they found out what the dog senses?
I don't know the one for epilepsy. I know what it is for diabetes. That's a really good question. If you come up with the answer, will you teach me? And if I come up with it, I'll teach you. For diabetics, when your blood sugar starts to drop or change, it actually changes the biochemistry, your cell chemistry. And the ketone bodies that are coming off on your breath are really easy to detect. It's the coolest thing ever. We talk about diabetes. And guess what kind of dogs it usually is? Golden Retrievers! Which are literally the best dogs ever. Do you know what, like, the last, well, I don't know about the last, late tier treatment for epilepsy is to keep that storm from going all the way from one hemisphere of your brain to the other? They cut your corpus callosum.
Oh, wow, really?
Yeah. They cut the corpus callosum and you become split brain. Yeah. What were you going to say?
I was just gonna say that's what I thought it was.
Yeah, they cut the corpus callosum. Yeah, it's definitely not plan A. So, probably plan Q. I don't know. I keep shocking myself. What the hell? Okay, so you guys got the whole EPSP, IPSP thing? Okay, so let me just tell you that there is another type of receptor that does the same thing, only it does it less efficiently. There's actually two more. I'm only going to talk about these first two. Okay, so these receptors, in which, stick with me for a second, the neurotransmitter binds to and opens an ion channel which changes the electrical nature of the cell, depolarizes or hyperpolarizes it. These are really quick to cause a postsynaptic cell response. Yes? Okay, these are called ionotropic receptors. Ionotropic receptors. The receptor is also an ion channel. You with me? Okay, so this is like making, if you're playing pool, this is shooting directly into the pocket, okay? But what if you want to really show off and you decide you're going to do a combo shot that involves 3 completely unrelated balls to hit the pocket? This is going to be slower, yes? It will accomplish the same thing. Notice here, this is an ion channel still, only this time the neurotransmitter binds to a receptor which slides 3 different proteins through the cell membrane to smash into the pocket, which is the ion channel. And that's how you open or close that one. This receptor is going to be slower to cause a cell response, yes? Yeah? It's going to be slower. It could still end up depolarizing or hyperpolarizing, depending on whether you open a channel or not. These are called metabotropic receptors. Okay? These are slower. Sometimes in your brain, efficiency is not so much about speed. So you will run into each of these as we go through. Unless I tell you otherwise, just assume that we're talking about the simple one, and then there'll be a few in which we talk about these as well. And we'll run into these again later. So ionotropic, the receptor is an ion channel. Metabotropic, you're showing off, right? You're like trying to make a 4-ball combo shot. I've literally never made one of those before, unless it was on accident, right? Okay, so you're okay with that? So the metabotropic receptors, yes? Not do you like it, but can you acknowledge that it exists? Yes. Okay, so let's go back to the ionotropic receptors and just assume that that's what we're talking about. So now the neurotransmitter stimulates a new graded potential in the next cell. Let's assume it's a depolarizing graded potential, yes? And it can set off an action potential if it depolarizes the axon hillock to threshold. Yeah? Okay, so, but we have other concerns. Let's go back to here for just a second. So, immediately after we release the neurotransmitter into the synapse and cause the desired target cell response, what we have to do is we have to remove the neurotransmitter from the synapse immediately. Otherwise, see if this makes sense to you. I can't quite figure out how to phrase this, but I think this works. If I release the neurotransmitter, I'm cell A, you're cell P, I'm going to release the neurotransmitter. If I don't remove it from the synapse, then can you see that she becomes insensitive to frequency coding? I just let it sit around there and it binds and releases and binds again and binds and releases and binds again, right? Because, by the way, the neurotransmitter binding to the receptor is loose and reversible. So what I need to do in order to make her sensitive to whether I am saying pain, 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 or pain, 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 what I need to do is every time the neurotransmitter, after it does its job, it needs to get the hell out of the way. So you can release more if you're trying to communicate more, right? So you have to remove it from the synapse almost immediately. So you release it, causes the desired response, you remove it from the synapse. Then you can detect whether I am yelling pain or just saying it, right? You can't do that if you leave it in the synapse because it'll continue to stimulate from the first release. So basically, the neurotransmitter, it's just as important to get it out of the synapse as it was to get it into the synapse. Okay? Does that make sense? You got it? Otherwise, how could you tell? If I release neurotransmitter once to tell you guys that something was warm, right? And it bound to you, and then it came off, and then it bound again, and it came off, and it bound again. How could you tell if I had released it 50 times over the same time period if you just let it stay around? So you have to remove it. And then the next time you'll release different neurotransmitter, and then the next time you'll release different neurotransmitter. Got it? So you have to remove it from the synapse. So the question is, how do you get it out of the synapse? So there are 4 ways to get it out of the synapse. The picture shows 3 of them. Okay, 1, if you're not really in a big hurry, you can just let it diffuse away, which is number 8. Okay? 2, very often the postsynaptic cell will have an enzyme present on the postsynaptic cell membrane, and that enzyme will change the shape of the neurotransmitter so that it can't reactivate the receptor. Okay, I'll give you an example. Acetylcholine synapses, most of them have an enzyme in the postsynaptic cell that's called acetylcholine esterase. And what it does is it pops acetylcholine apart into an acetic acid and a choline. Choline is more precious, so the presynaptic cell will take the choline back to use more of it, right? But if you pop it in half, it's not going to activate the receptor anymore. Okay, so the postsynaptic cell membrane will change the structure of the neurotransmitter so that it won't reactivate. There's another one called MAO, monoamine oxidase. Monoamine oxidase is present at postsynaptic cell membranes for norepinephrine and epinephrine, and what it does is change the shape just a little bit so they can't activate the postsynaptic cell membrane. So you got diffuse away, use an enzyme, and then the third one that's also on this picture is reuptake back into the presynaptic cell. So your cells are the original recyclers, right? So you released it, it did what it was supposed to do, and now you reuptake it so that you can package it again so that you can use it again. So that's a reuptake mechanism. Now, it's not going to cause a presynaptic cell response because of what you guys said, right? It's not interacting with the receptor, yeah? So you're just reusing it. Now, you may or may not know that you already know examples of reuptake mechanisms because Utah has, last year when I checked, I haven't checked this year, had the highest rate of antidepressant prescriptions in the country. And the vast majority of antidepressants are selective, serotonin, reuptake inhibitors. What they do is I want you to imagine that this is a serotonin synapse, okay? That's a neurotransmitter that's used at that synapse, okay? If my life sucks, or I have biochemical depression, or, by the way, you can get biochemical depression because your life sucks, right? Regardless, one of the things that allows me to have regulated moods so that when I get flat, I don't freaking cry snot bubbles on the side of the road, right? Is that my serotonin level has to stay relatively normal so that you can sort of deal with the bumps and bruises of life, right? So now have a sucky life or have some genetic biochemistry that makes your serotonin levels low. And what happens is it can manifest as depression and anxiety, okay? Which means when something happens, you have a very hard time weathering it. So how do you take care of that? Well, one of the most common ways to take care of it is to give the person, if we can't get you to make more serotonin, and we'll talk about how that can happen in just a minute, then what you can do is you can fake out your synapses by allowing whatever serotonin you release to stay in the synapse longer, which gives the faking impression of frequency coding, doesn't it? Because you released it once, but you use it 10 times. So what happens with SSRIs, selective serotonin reuptake inhibitors, is that for every serotonin release, you inhibit the reuptake right here at 7, and you let it stay in the synapse longer. And you get a relief from the symptoms of depression and anxiety, if your depression and anxiety was serotonin related. Does that make sense? So does that reinforce the thing that you were giving me the stink eye about, Casey?
Yeah.
Okay. Okay. What? I don't know what you're talking about. Okay. So does that make sense to you guys? Okay, and we'll talk about some other reuptake things. And then there's one last way that isn't drawn on here, one last way to remove neurotransmitters from the synapse. And they just figured this one out a few years ago, and I haven't actually seen it in the textbooks yet. But and that is that, remember, it's not just neurons in the brain, it's also glial cells. One of them is astrocytes. Remember astrocytes? I want you to imagine that astrocytes in this metaphor are the ball boy. Okay? So apparently what astrocytes do is after you release the neurotransmitter, instead of the pitcher having to roll it back to, the catcher having to roll it back to the pitcher, the astrocyte takes it and brings it back. Takes it and brings it back. Takes it and brings it back. And we only figured that out because somebody's astrocytes weren't working, and all of a sudden, like, the pitcher didn't have any balls left. Like, oh, I ain't got nothing to throw. And they thought, oh, it's making normal amounts, what's going on? What happened is it wasn't getting actually delivered the neurotransmitter back. Okay? So those are the ways that you commonly remove neurotransmitters from synapses. Okay, any questions? Good? Okay. Okay, so what we have been implying with these figures and sort of this story is that the relationship between neuron to neuron is one-to-one. And it's not. Certainly not in the central nervous system. You don't just have one neuron communicating with another neuron. It's usually more like this, or look at that and make 15,000 connections to a single neuron. So the question comes, how the hell does this poor little neuron ever know whether it's supposed to have an action potential or not when it's got all of these different inputs, right? And again, the green is supposed to represent excitatory and the red is supposed to represent inhibitory. So how does the neuron know what to do? Have an action potential? Don't have an action potential? I don't know. What happens is that the neuron, the relationship is actually, let's look at the relationships and then we'll figure out how it decides. So the relationship of one neuron to the other is usually more like this. When you have a whole bunch of presynaptic neurons all coming together on one postsynaptic, it's called convergence. And that should make sense, right? That's how you converge onto things. Yeah? And so when would be an example of where you would run into convergence? So I want you to think about your hypothalamus. Your hypothalamus, in order to set your metabolism, gathers information about light and temperature and metabolism and food availability. So you can imagine it gathering a bunch of information to decide what each little hypothalamus cell needs to do. So that's the idea about convergence. And then the other one is, this is divergence. Divergence, if convergence is many to one, then divergence is one to many. This is a bossy neuron. It's bossing all 4 of those neurons around as a team every single time it talks, okay? So this one, for instance, is how your neurons control like skeletal muscle fiber contraction. Like one neuron says, I want 500 fibers to contract at the same time, right? So that's called divergence, okay? So what happens with convergence and divergence is really the important part, where you actually care about, that actually decides what's going to happen in the cell, is the axon hillock, right? Because the axon hillock doesn't care how you got to -55. If you get to minus 55, you get an action potential, right? Doesn't matter if you had 10,000 cells that were telling you excitation and 5,000 that were telling you inhibition. As soon as you get to minus 55, you get an action potential. And it doesn't matter what occurred. So I want you to think about this cell as like your wake up cell. Imagine a cell that you've got that actually increases your metabolism and makes you wake up in the morning. And you've got different interests actually going to that cell. Some of the interests are, I only slept 3.5 hours last night. And the other one's like, I already paid for this damn class, right? I'm going to lose my job. You're a slacker. Whatever. So I'm exhausted. Nobody should live like that. All of these, and your alarm is going off. So which one wins? Well, whatever gets to minus 55, it doesn't matter how you get there. And then in addition, usually the most persistent one will win, right? You ever tried, like if you set your alarm to wake up, not just the snooze, right? When I know I'm not going to wake up, I don't set one alarm. I set 5 different alarms, and the last one yells at me and calls me a loser. Get up, loser! So it's persistence, right? A lot of times it's persistence. Which one is going to like be the most persistent in sending an excitatory or inhibitory signal? Okay, so this idea is that the axon hillock right there, it integrates or collects, and just if you hit minus 55, you get an action potential, and if you don't get an action potential. It's all about the axon hillock. Okay, so I told you guys before that research also shows that new synapses form during sleep. So you can actually reinforce a synaptic connection between the two of them. This is kind of an interesting thing. What if I used this certain pattern over and over again? What can happen? I know that we don't get any new axons, but what can happen is this axon is not limited at all in its ability to branch. So if, for instance, I use this one really frequently, what would happen is I develop a new branch off and another connection, and then a new branch off and another connection. Can you see that the more connections you have, the faster you get communication between the two of them, right? Because instead of releasing a single neurotransmitter at a single, what if I, instead of communicating to her like this, I communicated to her with all 10 fingers, all releasing neurotransmitters. That's a really fast connection. That's called synaptic plasticity or neuroplasticity. It's your capacity to change your brain based on how you use it. Okay, so next topic is related, and that is how do you get that postsynaptic cell to have an action potential? If this one had an action potential, do you always get an action potential on the second one? And the answer is no. And the relationship, so this relationship that I've been showing here in which, okay, get an action potential here, you release neurotransmitters, and you might get an action potential here. It's almost never a one action potential to one action potential relationship. What it usually is the presynaptic cell has to release neurotransmitters multiple times in order to get the postsynaptic one stimulated to threshold. Okay? And that means that there is a lag time, and the slowest part of your nervous system is actually your synapses. The action potentials go 250 miles an hour, but then you have to release neurotransmitters into the synapse, and then they diffuse across. But then it doesn't even take one time, right? So then maybe you have to release them 5 times before you actually get the next one. That little space in the synapse is the slowest part of your nervous system, and it works with what we call synaptic delay. It's delayed. How delayed is it? Between 0.2 of a millisecond and 5 milliseconds, but there is literally no way you could ever notice that because your noticers work with that synaptic delay. Like, you could not physically ever know that that is occurring, okay? Because the synaptic delay is sort of inherent in the system. That's how slowly it works. So that's called synaptic delay. It's what's actually going on right here. So now, many action potentials are usually required on the pre to get the post to threshold. Trying to get the post to threshold is called summation, and summation takes time. So let's look at a couple of different ways that you could actually get to summation. Okay, so we have in this picture, okay, these are excitatory synapses, and this one's an inhibitory. You guys with me? Yes? A, B are excitatory. Okay, so I'm just going to use A. I'm going to ignore B and C for a second. If I stimulate the postsynaptic cell with A, I get a small depolarization because that's a sodium channel. Okay? If I let it repolarize all the way back to minus 70 and then stimulate A again, I get no summation at all. But what if, instead of doing that, I stimulate A instead of A, pause, A. What if I went AA? Can you see that what you can do there is you can add to the depolarization, you can add to the number of open sodium channels and therefore make it more likely that you will get to threshold? This type of summation is called temporal summation. And temporal, other than the bone and the muscle, refers to what? Time. Yes, exactly. That makes sense? Yeah, it's related to time. So now, does it come up to anyone? I know sometimes the question comes up right here, but what about refractory period? Remember that refractory period doesn't actually occur until you get into the action potential. So graded potentials do not have a refractory period. And these are graded, aren't they? Graded, right? Graded big enough to hit threshold and you get an action potential. That makes sense? So refractory period is only once you actually enter the action potential. Okay, so this is called temporal summation. And if temporal summation is massive enough, then you can depolarize the axon hillock to threshold. And then there's one other way to do it, and the other way to do it is called spatial summation. And spatial summation, so let's look at what happens here. If I stimulate A by itself, little depolarization, no action potential. Stimulate B by itself, little depolarization, no action potential. Stimulate C by itself, definitely no action potential because I'm hyperpolarizing. But what if I stimulate A and B simultaneously? Yeah? They're both depolarizing? Yeah? So this type of summation is called spatial because you're coming from two different spaces or places, right? That's called spatial summation. Can you sum to -70 and not do anything? Yeah, if you're using A and C simultaneously, you'll just like not do anything. That's, for instance, when you've got like the cell that's getting two different inputs. Okay, does that make sense? Okay, so what is the fastest way that you can think of to get to an action potential? This is spatial summation. This is temporal summation. Anybody think about the very, very fastest way to get that postsynaptic cell? What? This is convergence, by the way. No, not that one. This one's convergence. Is there anything that says I can't use A and B simultaneously very frequently? A and B at the same time, right? That'll get you an action potential the fastest. So you can use temporal and spatial simultaneously. Now, to her comment, this one right here requires what? Convergence or divergence? Spatial requires convergence. Does temporal require convergence? No, temporal is one-to-one. That make sense? Got it? Okay. Okay, so that's temporal and spatial summation. And now let's back up a little bit and talk about some interesting, fun stuff to make this stuff relevant to you guys. Okay, so I want you to imagine that you have a neurotransmitter problem. And depression is the easiest one to think about because most of us know that depression is often related to serotonin. Okay, so I want you to think about your serotonin level and say, okay, I have been feeling really, really down, and not just because it's February, right? Everybody gets depressed in February. You're like, I literally am never going to leave my house ever again because it gets dark at 4:30 and I can't breathe when I go outside. What do you do? Like, what are the possibilities for managing a situation like that? So, modifying the synapses, modifying what's happening in your synapses with drugs and disease and behavior. So, I will tell you that we are constantly modifying what we do with our synapses. So, let's imagine that this is a serotonin synapse. So, you do all kinds of things because it forces your synapses to behave in a certain way. When you, for instance, eat something good, you'll release your most favorite neurotransmitters. When you sleep, you release some calming neurotransmitters. When you have sex, you release some excitatory ones, but also some ones that tell you everything's cool in the world. So you are constantly, whether you were a junkie or just a human, modifying your synaptic transmission. So I want more serotonin. I'm not feeling like I have levels of serotonin. How can I do that? Well, you can do it by sort of the inherent, relatively natural way of doing that. Like, one of the ways that you can increase your serotonin level is by starting to work out, by no longer surrounding yourself by butt heads, by getting more sleep, by eating good food. But of course, that is highly variable from person to person. It's not quick enough for someone with a serious depression problem. And also, we're really lazy, and that implies that I need to change my behavior, right? So plan A would be modify them by making yourself make more serotonin, right? Do we have drugs that make you make more serotonin? We actually have almost zero drugs that actually impact the levels of neurotransmitters that you make and release. And in part, that is because it's so difficult to get to an intracellular process and make it behave differently in a single subset of cells. Because serotonin is not just used for mood regulation, it's also used for hunger and sex drive and sleep and appetite. And also in your brainstem, it's used for hallucinations. So you mess with all of them and let's just see what will happen, okay? So we have almost zero capacity to modify how many neurotransmitters you actually make and release. So what's plan B? Plan B is interfere with the removal from the synapse, right? So if I can't make you make more, I can fib and make you think that you're making more. And so one of the ways to do that is by interfere with the removal of the neurotransmitters. So we already talked about SSRIs, selective serotonin reuptake inhibitors, Paxil, Prozac, and Zoloft, and a bunch of others. There's also SNRIs, which are selective norepinephrine reuptake inhibitors. These are your three favorite neurotransmitters. You don't know it, but they are here. So another way of treating depression is to let your norepinephrine go up a little bit. That's kind of your up-jazzed chemical. So SNRIs, and we'll talk about some SNRIs. Then you can also MAOIs, monoamine oxidase inhibitors. So monoamine oxidase was that enzyme on the postsynaptic cell membrane that broke down norepinephrine and epinephrine. So you could block that, and it would make you think that you had more norepinephrine, epinephrine, and dopamine. So that's another way of doing it. Or MDMA. MDMA is ecstasy, and it is used as a club drug and a party drug, but I don't know if you guys know this, but there are actually clinical applications for MDMA as well. One of the really dramatic ones that has had phenomenal success over the last 5 years is it treats really, really resistant PTSD. Post-traumatic stress disorder. They started using it in people who were victims of violent crimes, and now they are actually testing it on soldiers when they come back. So how is this one related to the story that we're telling? What MDMA or ecstasy, and by the way, this is in a clinical situation, you would be monitored with a medical professional, and you would not be given this as a maintenance medication. You would have it about once every 6 weeks with a therapy session immediately after. So what it does is MDMA causes, in addition, it causes a massive release of serotonin, super happy, and inhibits reuptake of serotonin. So you've got serotonin just flooding the entire brain for like 6 hours, right? And during that 6 hours, you also go to therapy. When you have massive amounts of serotonin, it reduces your barriers, your social barriers, and makes you more open to conversation. So you can get past that crap in therapy that you can never get past. And they thought initially that, oh, well, it's just going to like only work while the person is on MDMA. They will feel exactly the same. But apparently, the results have been solid. After 4 sessions, the results have still been solid for 3 and 4 years for these people. So it causes a massive release and inhibits reuptake. But you can't take that stuff very often, whether it's clinical or party drug, because what do you think would happen? Let's just imagine that this is a serotonin synapse and you took MDMA. So serotonin synapse, dump serotonin, inhibit reuptake, okay? Do that instead of once every 6 weeks. Now do it Friday, Saturday, and Sunday every week. Okay, or usually Thursday, Friday, and Saturday every week. And then can you imagine anything that starts to be a problem with the synapse, just hypothetically?
Is it not as sensitive?
Yeah, you downregulate your receptors. Yes. If you thought you were depressed before, downregulate your serotonin receptors and then release normal levels of serotonin, then you'll be depressed. Okay? In addition, when people use the SSRI, whether it's clinically or in a party situation, the problem with dumping it and then inhibiting reuptake is that you don't get to reuse it, so the cell has to remake it. Okay? So if you take an MDMA on Saturday, then after it's actually already flushed from your system and you haven't remade it, you are going to be really, really having a hard Tuesday. They call it Suicide Tuesday. Yeah. Suicide Tuesday is when your serotonin level is massively low. Don't make any big decisions. No divorce talks on Tuesdays, right? Don't tell your children that you've always hated this thing about them. Don't do that. Don't decide to buy a wombat. So you downregulate and you have to remake it all because you don't actually recycle it anymore. It's just like a massive dump. And when people are actually using it in a clinical situation, they have to come in for therapy on Tuesday. They got to come in because you're like, you're going to hate everything. You need to be here, right? And here, have a cookie. And your mom loves you. She told me. Okay, so now the other way is what if I can't manipulate what's happening in the synapse, maybe I can manipulate with the receptor. Yeah? Okay, so if I can manipulate the receptor, maybe I can take a drug that mimics the thing that I'm missing. Yeah? And so it would be a mimic. And this is called an agonist. Agonist is a mimic. So if I took a drug that mimics the activity, so it will bind to the receptor and usually cause a response that is similar to the natural response. And there are lots of drugs that do this. Most of them aren't neurotransmitter drugs. The one that is a neurotransmitter drug is kind of interesting. Nicotine. The reason people like nicotine, and I know it's so weird, people don't ever want you to tell them anything pleasant about any drug, right? Well, that's useless because you really need to know why people would want to do it in the first place, right? Like, it's not just people are like, oh, smoking makes you smell good. No, that's not what they do, right? So why do people initially find nicotine to be pleasant? One of the reasons is that nicotine is an acetylcholine agonist. And acetylcholine in the central nervous system increases short-term mental acuity and short-term memory formation. So when you smoke initially, it downregulates really quickly. When you smoke initially, you actually feel kind of with it. You're like, oh yeah, this is great, I'm smart, everything's good, right? And then it downregulates really quickly so you don't get that response anymore and you've already got the habit formation. So nicotine is an acetylcholine agonist. And then there are other drugs, and the other drugs are antagonists. Antagonists are blockers. If agonists are mimics, antagonists are blockers. And so let's say you were making, for instance, too much of something. You could stop making too much of it for whatever reason. Then what you can do is you can block the response to it by occupying the receptor, but occupying the receptor in a way that you don't cause the target cell response. Does that make sense to you guys? So here's an interesting one. See if you can figure this one out. So they occupy the receptor, but they don't cause the normal response. Caffeine is an antagonist, but puzzle this. Caffeine is an antagonist to an inhibitory neurotransmitter. So how can it cause the response? It's an antagonist to an inhibitory neurotransmitter. What? Yeah, it does. It causes excitation because it blocks the inhibitory response. That's why caffeine actually wakes you up, because it's an antagonist to an inhibitory neurotransmitter. Does that make sense? Okay, lots of antagonists, not caffeine, but lots of antagonists are poisons. If you happen to take in something that blocks the receptor and won't let go in a neuron, you can actually kill yourself with it. Pufferfish, do you guys know that people eat this as a delicacy? Usually in Japan, because you can't get it
You have to
here.
have a license to.
Yeah, so yeah, fugu is sushi that's made from the pufferfish. And, You've had it? I've literally never met anyone who's had it. And I went to Japan, and I couldn't get it because my husband wouldn't pay the $500 for it.
Especially if it's
What is wrong with that, man?
Especially if it's warm.
Oh, it's delicious.
I love sushi so much. So what this does, this animal has a gland. I always thought it was a salivary gland, but I think it's actually the testicular glands. And what happens is it has a neurotoxin in it, which is a defense mechanism for this fish, right? Okay. But this neurotoxin, so if you have a very, very carefully prepared licensed sushi chef, hard to come by here in the United States. I don't think you can get one unless you go to California. But in Japan, they're relatively ubiquitous, and it's really, really expensive because of the training. So they take out the glands, and then they prepare the flesh as a sushi, and then you eat it. And then in addition to being delicious, it also gives you a little tingle, and that tingle means you almost died. But you weren't bored, were you? Like, literally not bored for a couple minutes. So it gets a little tingle. And And don't think I won't try it. I like have an experimental personality. I'm like, I'm gonna die soon, and there's gonna be a big long story before I do it.
If you go to Okinawa, there's a chef there that also had a restaurant in California and New York, and sometimes he would go there to California and New York just to.
So I'm gonna try it at some point. And it was nice knowing you. So,
You should try it.
so that's fugu. Then there's a couple of other things that you can run into that are antagonists that you may have heard of. Have you guys ever heard of red tide? If you're from the South, every once in a while, the environmental conditions will be just right that you get this bloom of dinoflagellates, which is, I don't know if you remember that, what that means. It's like, kind of looks like between a germ size and an amoeba size. And these dinoflagellates produce a neurotoxin. And they make the entire area red. This is a picture from Texas, by the way. So it has to be relatively warm, so it's going to be like closer to, the equator, not in the far northern hemisphere. So they produce a neurotoxin that is so powerful that you can't eat anything that comes out of the ocean for like weeks on end. So it destroys all the shellfish. You can't swim in there. It irritates your skin. If you actually ingest it, it can cause neurotoxin activity. You can't eat anything. So this is red tide, which is a neurotoxin, and it's actually a neurotransmitter antagonist as well. And then the last ones are, these two are not as likely to kill you because they stay local. Honeybee venom is a neurotransmitter antagonist, but it stays local, right? So it doesn't like go into your bloodstream. Same thing with sea anemone. It's a neurotransmitter antagonist, but it stays local. But black mamba venom, that'll kill you. It's a neurotoxin. It actually attaches to your neurotransmitters and doesn't let go. So don't play with that. Black mambas? Black mamba? Big old snake?
Kobe Bryant was black.
No, not Kobe. I wouldn't play with him either. He's kind of dangerous. Heard some stories about Kobe. I don't know. Okay, so let's start our little tour of neurotransmitters. We're going to learn the major neurotransmitters, and we're going to learn drugs and diseases that have to do with each neurotransmitter. This is my favorite book. This is my neurotransmitter Bible. Robert Julian is a neurophysiologist. He puts out a new one of these every 3 years. It has, in addition to every known neurotransmitter, it has every neuroactive drug, including things that you don't think of as drugs, like glucose, and things that you do, like crack cocaine, and things that you take, like opiates. So it has all of them and their action in it, and most of the stuff isn't in your textbook because I like this stuff and I cover it more deeply than your textbook does. He also, by the way, he puts out a new one of these every 3 years. They're like $70 a piece, but his Kindle one is $12. He's got a Kindle one online that's $12, which is searchable, right? You can search anything on Kindle. I love it. So I get a new one, Amazon. And there's a link on my links page to it if you want it to. And no, I don't get kickback either, so shut up.
Oh, I've seen that one too.
That stupid thing. That was Chelsea, my best friend, always texts me when I get bad reviews. Jerk. She's like, apparently you're getting a kickback for your clickers. I'm like, literally F off, all of you. That's why I live so high on the hog, right? That's why I drive a 12-year-old car, because of my kickbacks. Okay. Chemical neurotransmitters are chemical messengers that are released from where? Close to where? You tell me. Neurotransmitters released from what? Close to what? Neuron, axon, yeah. Neuron close to where? Receptors, exactly. That's what makes it a neurotransmitter. So these are the communication mechanism in the nervous system. And so let's talk about what I mean when I say a CNS neurotransmitter versus a PNS neurotransmitter. A CNS neurotransmitter is going to communicate between two neurons in either the brain or the spinal cord, yes? Okay. Those are the most fascinating ones because, of course, they have to do with mood and intelligence and emotion and appetites and all of that kind of stuff. So those are really interesting, but we know less about them than we know about the PNS neurotransmitters. And the PNS neurotransmitters communicate between a neuron and something else out here, usually a gland or a muscle. We have a lot of knowledge about these because we can manipulate them, right? I mean, so if I said, okay, I know someone who's 15 IQ points higher than I am, and I really want to figure out what's going on, will you please let me experiment with your brain? Will you? No, but would you let me zap and see acetylcholine release right here? Yeah, totally. I'll do it in lab, no problem. So in addition to not having the capacity, because of the whole human rights thing, to manipulate other people's brains, willy-nilly, we also don't have a good animal model for higher functionality in humans, right? So how do you know if a rat is super duper depressed? How do you know? I don't know. You can look at like a couple of behavioral indicators, but it's really no way. And then you can't, for instance, directly compare those kind of higher functionality. So your central nervous system neurotransmitters, although we're the most interested in them, we know the least about them. Now, we do know a lot about them now. We know where individual neurotransmitters are used. But what we don't know, and this is humbling to think about, is if you go into the doctor and you say, I am really depressed and anxious, does your doctor ever test your serotonin level before giving you an SSRI? No, they have no capacity to do so. Does your serotonin go into your bloodstream at any level that's detectable? No. And remember that it's released and almost immediately reuptaken. However, if I went into the doctor and I said, I think I have a thyroid problem, they test your thyroid hormone in your bloodstream and they treat based on that. So what are they doing with SSRIs? They're experimenting on your brain because you told them you wanted them to, right? So you need to be involved in the process, right? You need to say, okay, well, I know about downregulation, so I'm going to take the lowest dose possible, and I'm going to write down everything about how I feel, because then you go back, and then they're like, is this working for you? And that's almost all the conversation you have. How's this working for you? Well, I write down everything. I'm like, I had trouble sleeping this night. I'm not interested in sex. I gained 15 pounds. I want to reduce the dosage by half, or I want to try this one, or I want to try that one. Because you are the person that is the most educated about your brain functionality. You really are. Certainly more than a general practitioner, especially after you get finished with physiology. So they are CNS neurotransmitters and PNS neurotransmitters. Now sometimes some of them are both, right? You'll use it in the CNS and the PNS, like acetylcholine has CNS function and PNS function. And so what they generally do, I mean, there are exceptions, is they'll bind to and open an ion channel and cause an EPSP or an IPSP. That's usually what they do. There are at least 60 that we know really well. You don't learn 60 because we don't understand them well enough to make you learn them. I haven't counted them up yet. I'll see how many you guys know. Now, what is a neurotransmitter like? What is it chemically like? Well, it's going to be relatively small, like a mid-sized, usually water-soluble. Not all of them are water-soluble. Let me show you. So these are all amino acids, and neurotransmitters are usually about the size of an amino acid. And so, for instance, here's acetylcholine, right here. All of I don't know if you've taken organic chemistry, but all of those are carbons if they're not labeled. So you could actually count all the atoms up, right? And you wouldn't get too bored before you finished. So usually mid-sized water-soluble, and the small matters because if you're enormous, how quick is your diffusion across the synapse? It's going to be slower, right? So they're relatively small, they're low molecular weight, they're usually fast-acting. Even the biggest neurotransmitters are only about 8 or 10 amino acids long. Not like hundreds, like with a quaternary structure, like a peptide or something. Does that make sense? So that will matter. So they usually have more than one receptor subtype. So for instance, there's not one acetylcholine receptor. There's at least 2 subtypes, and there's subtypes under them. I won't make you memorize receptors unless they're like really clinically relevant, like the one that's involved in addiction is a good one to know. And then the other thing is that the response to a neurotransmitter is usually tissue specific, because if I release serotonin in a certain portion of my brain and it causes mood regulation by inhibiting activity, that doesn't mean that I can't release it in a different portion of my brain and it will cause excitation, right? So the response is more about the receptor than it is about the neurotransmitter. And you use them for multiple different functionalities in your brain. Does that make sense to you guys? Okay, so what we are going to do next time is we're going to start like the tour of neurotransmitters. And 3 of the neurotransmitters that we will talk about are the 3 neurotransmitters. These are the biggies. These are the biggies with mood and happiness. serotonin and norepinephrine and dopamine. I'll just give you a quick and dirty introduction to each one of them, and then we'll get into more detail about them. Dopamine is your reward neurotransmitter. When you do something that evolutionarily should have been rewarded, like for instance eating something good, your brain releases a very pleasurable chemical that is your brain's way of saying, that was awesome, do that again and frequently. You can see that tapping into the dopamine pathway would both be very, very pleasant and also potentially very habit-forming, because it is a reinforcing neurotransmitter. Almost every drug of addiction taps into the dopamine pathway, okay? Serotonin is your regulatory, right? It allows you to weather the bumps. If you have too low, you have a lot of trouble with it, and too high causes other kinds of problems. And then norepinephrine is your sort of, I'm with it, I'm awake chemical, right? It's like I'm alert, I've got concentration, I've got energy, I've got memory, right? So the ideal middle of that Venn diagram right there is that's your sweet spot, right? You got enough serotonin, enough dopamine, and enough norepinephrine that you can get all your crap done, feel really good about your life, and be happy, right? Anybody sit in that little middle of the Venn diagram? I've been there once. I remember it, right? It was cool. And then I was like, who is this? Oh my God, somebody has taken over. So we will stop there for today, and we'll start the tour of neurotransmitters next time. You won't have a quiz until a week from today. Everybody's so damn quiet the day after a test.